All right, we are on day 17, Clumsy Crucible. Okay, lava's flowing. The reindeer offers you a parachute. You descend. Half of Gear Island is empty, and the half below you is a giant factory city. The lava's filling. The lava ducts will carry the lava through the city. What is a crucible? Was that just a cup? Crucible is basically a large cup. Top heavy and pushed by hand. Difficult to steer at high speeds. To get Desert Island, the machine parts it needs as soon as possible, you'll need to find the best way to get the crucible from the lava pool to the machine parts factory. To do this, you need to minimize heat loss while choosing a route that doesn't require the crucible to go in a straight line for too long. Fortunately, the elves have a map. That's our puzzle input that uses traffic patterns, ambient temperature, and hundreds of other parameters to calculate exactly how much heat loss can be expected for a crucible. And okay, so this is the heat loss for each position, it looks like. This is sounding like, all right, this is the pathfinding day. Each city block is marked by a single digit that mounts the amount of heat loss if the crucible enters that block. So if we enter this, we lose 3. The starting point, the lava pool, is the top left city block. So it's 2. The machine parts factory is the bottom right. So it's 3. Because you already start in the top left block, you don't incur that block's heat loss until you leave that block and then return to it. Because it is difficult to keep the top heavy crucible going in a straight line, it can move at most 3 blocks in a single direction before it must turn. We can't reverse. We can only go forward, or we can only go left, straight, or right. This is one way to minimize. What is the least heat loss that can occur? Okay, so there's 2 approaches that I've used for this in the past, especially when it comes to advent of code. We've got the pathfinding crate and the pet graph crate. The pet graph crate would allow us to build up from our input basically a graph of all of the nodes and their costs, and then there are algorithms, as you can see here on the left, pet graph, algo, min spanning tree, etc. And you can just run that algorithm on petgraph. And this works very well. I've used it in past years. It's also something that I've used to represent graph data structures for applications like you might see in Blueprints or in another shader editor or DaVinci Resolve, where it's kind of this like, wow, that doesn't show me the image if I click on it. That's unfortunate. Anyway, it's this like node and these connect at these dots, and then it's got a couple of inputs and a couple of outputs. So this is basically a graph, right? So you could represent this as pet graph, visualize it with something like eGUI, and also do things like pathfinding or whatever we're doing, shortest path algorithms, things like that. The other crate that people use every year in Advent of Code is pathfinding. Pathfinding implements several pathfinding algorithms, such as A*, depth first search, etc., etc. This is one that people use a lot every year. You'll see that this is an algorithm for finding the shortest paths between nodes in a weighted graph, which may represent, for example, road networks, like exactly what we have today. So I do like petgraph, but I've used it before. So I think today what we're going to do is use pathfinding. I think that we only have one path to find, so I think this one's going to be right for us. So we're going to want to try to use this module, which looks like we get a starting node, the successors for the starting node, and the success condition, which is the final node, I believe. The success checks whether the goal has been reached. So FS we can see is a callback. Successors allows us to produce the list of successors for each individual move, which will allow us to prevent backward movement. And it gives us a little example here. So this is basically what we're going to do. And then the only adjustment to this algorithm is we need to keep track of like the last 2 positions as well, or the last 3 positions. And if we need to go, let's say straight again, we need to take straight out of the equation so that we can't use it. And then we just run that and it should give us an answer. So let's get started here and let's pull in our example. We'll just create day 17. That's the day we're on, right? Day 17, input 1, all set up, part 1, get our input in here. So we can be very fancy with this, right? And we can convert this to a byte slice, effectively, use as bytes on it, and use that to index into it. I think that I'm going to take a less efficient approach. Let's see what we need to do for this code here. So let's paste the example code in here. This is obviously not going to be quite what we want. So successors here is returning a vec of positions and use sizes. So this position is effectively ivec2s for us, or will be. So this function is designed to give us the next nodes. So I think what we're going to do here is build up that B-tree map that we're so used to at this point. And I'm going to remove that code. We will have to add the pathfinding crate because we haven't used it yet. And this is currently, if you go onto the page for pathfinding, you can look up here, copy this, 460 is what we're at currently. Then we can just paste that right in, pathfinding 460. That comes right out of the docs. So you can just copy, paste, be done. So for part one then, I want to parse everything out. I think I'm going to reuse the nom-locate stuff because that will give us all the locations. It is a little bit overwrought for today, I think, but I'm going to be okay with that. We're not looking to build the fastest parser. I personally am looking to build something that I can come back to later and understand. So let's span IVEC2s. We don't actually really need to parse these. I guess we could parse the numbers. We will need nom-locate and glam. We aren't doing really like intense grid work today. So IVEC2s, if we didn't have glam already sitting in our crate, I might not use it, but I do find it very useful to be able to do .x, .y, and IVEC2s are not expensive for us to use. So if we get a separated list, line ending, many one, I guess not any car. Does bytes have a take? Bytes has a take. Returns an input slice containing the first n input elements. So in this case, it'll be 1, but for us, it'll be, or in their case, it's 6. For us, it's 1. I think that will work for us. And then we'll many one take. I don't really want take 1 though. It leaves a little bit of a bad taste in my mouth parser wise. So I think I'll use one of these numbers, right? And then we want that there. There is an issue here. Let's get our check going. I think it's the nom-locate and the, yada, 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 separated list, line ending, many one of. I think we'll need to make use of position for this, right? Where we do something like this inside of a different function. So we get one of these. Input, right? Let input n equals this. And then we don't have with xy here because this is just going to be a character. Wait, did we not bring in? Okay. Do you need to bring in position from nom-locate? I've done something wrong somewhere. Oh, I changed the name of this. Whoops. Make sure that your inputs and your output types all match when you're using nom. I don't know why I made that mistake. Just a little brain fart. So these are all going to be single digits, right? If we look at our input, I don't think we can handle anything more than that. So this could be a U8, and instead of using this on our parser, we can stick this in our parser directly here. And instead of doing this, we're going to have this, and this is just going to stick right there. And I think this is actually going to be before that. I think we're going to have to look for the cost by the address. So this is going to be okay. And the output type here is going to be an IVEC2 and a U8, I suppose. And I guess we'll call this POS because that's what we have it called. N doesn't need to parse into a U8. We get to do 2-digit here because it's a character, which is wonderful. We're going to unwrap that because it's always going to succeed. I guess that brings in an I32. So we'll use an I32 here. Found U30? Oh, it's a U32 because of this. What's up? I didn't include the input for the output here. So we're getting a little bit brain fried at the end of Advent of Code here. Making a bunch of typo mistakes over the last couple days. So here we're getting a result of IVEC2s and U32s, right? So if we have many nums separated by line endings, then this should be a vec, and we can output.iter.flatmap, and then we get a vec of I30 or an IVEC2 and U32s, and we just iter here, and we collect that into a hash map of IVEC2 and U32, and this is effectively our grid. I guess we'll iterate this because we don't really need any of it to stick around. So we get all of that. That's our map, right? Hash map IVEC2 U32. And then we take this type and we put it as our return type. And we don't really need span IVEC2 today because we're just doing span and then we're using the information we get from it. But that should give us all of the positions. So let's see if that works. So we print line, we use a grid. We have to make sure that we are using our variable here and that we are creating the span because we're using span as our nom input type. And then we are checking and not running here. I think today is a day where we might not have any infinite loops. Okay, so we get everything here. 410 is a 4, 610 is an 8. Let's just take a quick look. 0, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And then what? 4 over 0, 1, 2, 3, or 1, 2, 3, 4. Is that right? Check something a little bit higher. 7, 0 is a 2. 0, 1, 2, 3, 4, 5, 6, 7. That seems off. Let's debug 0, 0, and let's do 1, 1, and not print out the entire grid. Column -1 and position -1. I messed up the parsing somehow. What did I do? Is position different based on how we used it here? That's interesting, right? So if we do the position first, do we get the values that I expected? 0, 0 is 2, 1, 1 is 2, right? 0, 0 is 2, then 1, 1 is 2. So we need to do the position on the initial. Let's make sure, I guess we did the next row, so that works. Let's do 1, 4 just for another sanity check. 1, 4 is 5, so 0, 1, 2, 3, 4, 0, 1 is 5. Yeah, okay, so we're good now. It was just a matter of where I put that position. So it seems like the position runs before the parser, which is not a feature of nomlocate I've used before. I haven't needed this position before. So that's interesting. But now we have everything in a hash map and we need to use pathfinding. This builds up a whole struct. I don't think we need that. I think we can just write this in line. So we need these and this will go right in here and we will bring pathfinding out to up here with everything else. Get rid of some of these unused imports. And then what do we have to do? We have our goal. Our goal is length, right? So let's do the columns and rows again. I put this in parse grid for some reason. Not sure why I did that. Pulling that out, putting it into process, which is where I want it. So we have the grid here. Let's do row count equals exactly what we did yesterday, right? So we'll just copy yesterday's code and bring it in. So we get row count, column count. I guess we don't need these as I32s because we're using them as, I guess we do need them as I32s if we're going to use them like that. So we get this. Our goal is going to be XY. So column count and row count, which I'm just going to verify. And I'm going to comment this out for a second. Oh, this is a static. We don't really need this to be static. All right, so we can debug our goal here. And that gives us 13, 13. Is that accurate? 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. We need -1 for each of these, which does make sense. So 12, 12 is our end goal. I guess what's the answer we need here? What is the least heat loss it can incur? So the result here is a vec of nodes, so we can just calculate that afterwards. So we need our start node, how to generate the successors. So grid.get ivec2 new 0, 0. And we could use splat here if we wanted to shorten that. Unwrap, because this will always exist. This has to be a reference to do that get. And then we don't get XY here. We're just going to get a position, which is going to be, I thought this was going to be an ivec2, but the types aren't telling me that it is. And this is a U32. What does successors get then? Successors returns a list of successors for a given node. So we should get a node here. I'm assuming that this is supposed to be an ivec2, right? Something like a double reference to an ivec2. So we'll to do in here for a second. And then this is not going to be P equals goal because P is going to be a node, right? If we look at the types here for successors, FN gets a reference to a node. Yeah. And this is supposed to give something that can be itered over. What is C? Cost? Oh, this isn't going to be grid.get position. That's why everything's a U32 because there we go. Now we have ivec2s for everything. Wonderful. Okay. So I guess we don't need to grid.get, do we? We need to get the next ones. So we need plus minus in all directions. So we need what? 1, 0, -1, 0, -1, and 1. So we need each of these positions. If we iterate over these and map, we get a position. We do pause plus position. I guess we could do an early filter map here if this doesn't like exist, right? So we get this new ivec and we to do if ivec is outside grid, filter out because we can't go in that direction. And then we also to do can't go backwards, which means we need to be keeping let mute. Let's do a vec deck here. So let mute last positions, right? Equals a vec deck from, I guess, ivec2 splat 0, right? Because this will let us push off the back and pop off the front or whatever. I guess this does need to be from an array or from something like that if we're going to start it like that. So we've got our positions. These need to be added together. What is the problem on that right now? Oh, right. We aren't giving back the cost right now. So expected, whatever. Then I'm just going to take these positions and I'm going to return the position and the position from the grid, which always has to exist because we've already filtered everything out. And I think that should be what we need, right? An ivec2 and a cost. The trait 0 is not implemented for reference to U32. So we get a real U32 there. My big question is position or lifetime doesn't live long enough. Has type reference to filter map, some position, nested closure. Oh, because of the grid. Closure contains a lifetime. Lifetime may not live long enough. Wants us to put a move on positions. variable does not need to be mutable because we aren't even using it yet. These are owned IVECs that we iterate over, that we're filtering and get rid of, that we then use. It's not going to be just like collect this, right? I don't know how this whole function works yet because this is my pathfinding introduction. So type must be known at this point. I think the result is what, a vec. Our result here is an option vec of n and the cost. Oh, we get the cost? Nice. So these are going to be IVEC2s and U32s. And then this collect probably can't build because we have some references. Again, collecting because makes everything easier to type out. We can always move backwards to something that is or not as allocation heavy later. So we've got this so far. We are obviously failing because we are unwrapping on a none value. We need to filter out the positions that don't exist. So do we have the boundaries? Did I make that already? Let boundaries equals IVEC2 new column count, row count. So if 0 dot dot boundaries dot x contains position dot x and 0 dot dot boundaries dot y contains position dot y, then we can return this type. So right now we have an issue where we have references to I32s, which are expected here. We also need to else this. So if it's within the boundaries, then we can use it. Wait a second, we need to do this first. Let next position equals this. And this is the one we need to actually use. I don't know why I was using the other one. We need to check if the next position is in the boundaries. If it is, then we can use it. If it's not, then we have to go none. We also can't go backwards. So this would be like another and. So we have to decide whether the front or the back is what we're going to push on for this vec deck. But once we do, we can just say back or front. So in this case, I'm going to do back. I actually think now that I contemplate this isn't going to work because we need to keep that state around. But we can't do that here. That's really unfortunate, actually, now that I think about it. I don't know why I didn't think about that earlier. This random, like, we can't go straight 3 times rule really chunks it up. We don't have access to the previous path here, do we? We just get a node. That's really unfortunate. Oh, that's really unfortunate. Okay. So actually, we may have chosen the wrong crate, honestly. Dang. So in PetGraph, we could implement our own traversal, but this is actually not going to work because we can't keep any state for each path. Oh, that is so annoying. So how do they implement this? Maybe we were meant to use A star all along. Start successors heuristic. What does heuristic get? FH gets a node. Not good enough. Well, that's unfortunate. Okay, so I was thinking through how to deal with this going backwards and also the 3 tile path solution or deal. And I think that we don't trek backwards in the algorithm. We don't need A star. I was looking into A star. But notably, a node will never be included twice in the path. So we can't backtrack anyway, which is fine. So the backwards is already taken care of for us. The issue is we then need to, after we do everything, like this last positions thing that I was going to do does not work because we do not get access to each individual path with its test until afterwards. So let's see if this works to start with anyway. And we may have to go back and actually re-implement this whole thing ourselves instead of using this approach. But the backwards requirement is already handled for us. If it's outside the grid, we do need to filter it. Otherwise, we continue. We're down at to do. To do is great. Unfortunately, this also only gives us the shortest path, and we need to start culling stuff. Oh, this is really annoying. This is literally a puzzle designed to be annoying. What if instead of doing this way, right? Because we have additional requirements, right? So what if the nodes actually included more information? If we can revisit each node, then the nodes are effectively new nodes when you see them next. So instead of just being in IVEC2, right? This node to start out with is the position, something like either the last move direction or the last couple moves. I guess starting at 0, we don't have a direction, unfortunately. So I guess it starts out as none. And then, or is this just like a vec? So it starts out empty and we just push a couple of them on, and this is our vec deck instead. So then this gets position and our deck, right? Why is that not happy with me? Is that because I typed this incorrectly? Because this is going to be now a vec of IVEC2s and a vec deck of, what are we using here? I32s, U32s, U32. And then the goal down here, of course, is going to be that vec and the deck. And this is win equals goal. And I guess this is technically to do not too far in a straight. And then the deck needs to get passed into everything. That's annoying. But this collection needs to happen that way. So there's going to be a vec deck of U32s, right? And this can't be produced from that yet. And we need this to be position and the deck. And I guess this is going to be, it's just an IVEC right now. So this is going to be next position and like the new deck. So vec or the deck push front position, right? So we clone that just to make a new one. Then the new one's mutable and we keep that around, right? And then I get to take this out because that is both of them. And now I've probably messed up my types somewhere. So this is an IVEC2 and a vec deck. And the errors we're seeing here are value of type IVEC2 vec deck with a U32 cannot be built from an item of IVEC2 U32. That's totally valid. Why do we have that? Why do we have that? Because we're mapping over this with the grid position. That seems fine to me. Yeah, that's a tuple of the IVEC and the vec deck. So if we run this and we look at it, changed to IVEC2 U32 here, that doesn't seem right. Iterator item remains IVEC2 here. Iterator item is IVEC2 here. Filter map. Shouldn't the filter map be giving us what we want here? Oh, this is just the vec. Wait, filter map should be giving us this tuple. So we have IVEC2s, right? IVEC2 into iter filter map. This is just the position, right? Which is an IVEC2. And this is position.0 because this is the deck. I put that in the wrong spot. So that's the deck. Then we push front position, right? Which is probably a reference. Yeah, it's a reference. IVEC2 cannot be dereferenced. Do we, I thought, oh, is it an IVEC2? What did we say this was? IVEC2 deck. And the deck is U32. No, the deck isn't U32. The deck is IVEC2. So that's good. But this is IVEC2 because that gives us all the positions. This is already, so grid.get then needs an IVEC. And we are using not an IVEC. So we need to get that, which is going to be a reference, right? I don't want to be doing this deck as a reference. Borrowed after move here because we put that here. So let's pull this out. The next cost is that. And then why is this a reference? Filter map. Deck is a shared reference, so it can't be mutable. Why is deck a shared reference? Oh, because I'm still accessing the old one. That's great. And then we have the data moved here because it's a vec deck, which doesn't implement copy. We don't want to dereference that. And then it's not win equals goal. It's win equals shared reference to goal. And we don't actually use the deck here because we don't need to. Then we run this and we get an infinite loop, probably, or something that just runs for way too long. I don't even know what loops would be here. I guess technically the way this is written, it could just go forever, right? Dang. Oh, you know what we aren't doing? We aren't doing the check. We aren't cutting it off if it goes 3 in a specific direction. So filter map position, right? We've got the deck here. So if we have the deck and we iter over the deck, and so first of all, if the deck.length, I guess we aren't pushing things on either. If new deck.length, what is it? Equals 3? Do we need 3 total? Pop back? I guess that's 4, right? Because we only need 3. So if deck length is 3, then we could hit the condition where we've gone 3 in a row. Wait, no, if it's 2, right? 2 or greater. So we push here. We've already done the work. So let's do it here. If new deck length is 3, because it will only be 3. New deck.iter.map position.x, right? .unique, which comes from iter tools, I think. No, I don't want to extract that into a variable. Deck.iter.map position.x, right? That's an IVEC2 position.x. Unique. It is the unique function like that. Method not found in map because iter tools isn't in scope. And then this is going to be a unique.count. I guess this is the full thing here, right? So it needs to go here. This would be num straight x. This is just going to be real silly because I'm still working out whether this is even going to work as a whole. So num straight x, num straight y. If num straight x equals 1 or num straight y equals 1, then none, right? Otherwise, pop back and otherwise we sum. And that runs and then panics at not yet implemented, which hopefully is a good sign, honestly. So what is our shortest path then? The result? 102? Is that? That sounds way too high. Oh, it's 102. We did it. We did it in the most hacky you know, whatever way possible. Okay, let's do this. Okay, result.toString. I thought, oh, result.one.toString, because this will be cost, right? What is, okay, what is result? Let's get rid of the debug on that. What is result? Result is an option of a vec and a U32. So if this, let's expect this should have a valid path, of course, because all of this is wrong now, because this needs to be not an option. The shortest path is not an option. Okay, and this was supposed to be 102, so I'm just going to put 102 there. Okay, so that works. Let's run this on part 1. Let's run in release mode because, ooh, I hope this runs quickly. 1126. That's not the right answer. It's too low. Damn. Is it plus the... I don't know how to test this now because we got the right answer here. I wonder if our vec deck needs to actually hold everything. Because right now we're doing if the length equals 4, which means we are in the 4th position, right? That doesn't sound right. Okay, let's check the... It can move at most 3 blocks in a single direction before it must turn. So 3 blocks in a single direction would mean that this 4 has to be 1, 2, 3, and then the one we're trying to go to is 4. So I think that's actually good. The issue with that is that we're popping here. Let's panic and see what happens. So new deck is 1, 0, 0, negative 1. 0, negative 1 is outside. That should never happen, right? We're doing that check if the boundaries contains X and the boundaries contains Y, then we continue. Otherwise, none. We should never have a negative there. What? Why would we have a negative? Okay, if this, otherwise that, right? This is none. This does not get through. And this is on next position. And this needs to be pos.0. I mean, it doesn't need to be, but why do we have a negative there? I don't see anything coming through here that's negative. Pos.x, pos.y, num straight. Why does the new deck have a negative y? We don't do any math on them, right? Next position, pos plus, deck.clone. I feel like this is the answer here. Let's see. Filter map pos, right? We never get a pos that's negative. Somehow we get a vec deck that's negative or has a negative, but why? Right, because this position has to have come in at some point. The only way we get that is from these. These go through this, which means they have to show up here. However, when we look at the next position, legitimately none of the ones that have shown up are negative. So where did we get a negative 1 here? How did we get one? Let's debug deck, right? So 1, 0, right? Deck empty, 1, 0. And then from 1, 0, right? So I'm assuming we're at the 4. We can go 0, 1, and 1, 0. So this will also go 0, negative 1, which is wrong. How do we get from 1, 0 to negative 1, 0? We literally cannot because we're not supposed to go backwards ever. So if we're at 1, 0 here and our deck says we were supposed to go negative 1, 0, I feel like these are just using the exact value. So let's look at our addition issues here. So we've got 1, 0, negative 1, 0, 0, negative 1, and 0, 1. These are all of the places we can move to from where we are. At position, or rather at position, we can have a pos diff. I guess we should call this pos diff. Because we're pushing front pos diff, and we need to push front next position. That makes so much more sense. So small bug. How did it work for the test? That's my real question. 1236. That is a viable... Actually, let's run the test first before we do this, because I don't have any idea how that worked. 102, 113. This has got to not be 1236. That's too high. So at least we have a boundary. So we got too low and too high by about 100. And this is minimum. So we are validating that wrong. So we've got another bug here, whatever it is. I feel like I want to view the path it took or what it thinks of as the shortest path. So we're going to get a vec of ivex, right? So let's do print path here with 0 and then all of these. So 0.iter.map, and this is that. So it's going to be .0, right? Collect hash set iveq2, fn print path, hash set for iveq2. And then we already have a print grid, which I'm going to probably take and look at. Here's a print grid from previous day. Just going to pull that in here. We do need these boundaries. And in this case, if we get one, we're doing hashes and dots. I think that's okay. Do we know what the optimal path is for the test? Here we go. So it's 1, 2, 3, down, 1, 2, 3. Oh, it's moving in a straight direction. It is not. Okay, that's our issue because we need to go one more to the right here. Visualizations for the win. Okay, so let's do what? This test is wrong then. So if we, num straight x, if we have 4 elements, is not necessarily if they are all in the same x position, because it matters how they got there. So maybe we try to clear this whenever we change positions. So can we guarantee that the vec only grows if it goes in the same direction it did last time? We need to keep the direction around anyway, I think. Well, I guess we can do this without the direction, right? Because we have the deck, and if our deck is not cleared, right? If our deck only has 1 element, then that was our last position. Out of bounds access. And then we panic in here just to make sure that that stops. So what? 0 is the far end, or 1 is the far end. I should have done 0. Why did I do 1? This is what I should have done. Front. So front is the furthest place we've been. Are we pushing back? No, we're pushing front. So we went from 0, 1 to 1, 1 to 2, 1. So front is the right place to check. But we need to know the diff between middle and front. So 1 and 0. And then we need to know the diff between 0 and where we're going. And if that is the same direction, then we need to check. Yikes. So if we debug this, we should see like a 1, 0, negative 1, 0 kind of deal. Negative 1, 0 here. So we know we went west. So we need at least 2 elements here to have had a last position to care to check against, right? So if the length of this deck is, well, first of all, let's get all of the calculations. So we need 3 minus 2, 2 minus 1, 1 minus 0, and then we'll need to check 0 and where we're going. So that requires 4. That requires a 4 element deck to check. So I think this has to be 5 if we're going to do the check here. We take this and we basically say if the deck length is 5, then we need 1, 2, 3. We actually need all 4 of these to happen. And if they're all equal, then we none. If we've moved in the same direction, that is 4 times in a row, we're done. But to do that, we need a length of 5 because we need to check 0 to 1, 1 to 2, 2 to 3, and 3 to 4. 0, 1, 1, 2, 1, 2, 3, 4, 5. So let's let the direction equal this. Let's set this up as an array that we iter over that all have to pass this check. A dir equals dir. And this is an absolutely awful way to write this. I can already tell. And not just because my auto formatter broke. Typically, my auto formatter breaks if I have done something that is so nested or so egregious that it just gives up, which is kind of where we're at right now. That's just the vibe today. You know what? Sometimes that's fine. So 3 forward check here, right? If we've moved in the same direction 4 times, that's this check. So we don't need num straight, and we can do if 3 forward check none. And then we can run our test and fail everything again because I left a panic in. Out of bounds access. Really? Did I leave something in here? Out of bounds access on 90 here. If we have a length of 5, shouldn't that work? 1, 2, 3, 4, 5. If we have a length of 5, and it's actually not going to be a length of 5, right? Because are we not popping? We do still pop. So let's get rid of that. I guess not get rid of that. I don't know. We only do that in certain cases. So 0, 1, 2, 3, 4. How is that out of bounds? And it said it's this one, right? Oh, that's because I didn't change the name of it. That's silly. Let's get rid of that debug because that debug is gonna hurt us. Okay, so that is 100 and that is wrong as well. 1, 2, 3, 4, 5. I guess we don't really need 5 checks, do we? We need this one, right? This is the next one that we're going to move. This is 1, 2, 3, right? If the last 3 movements were all in the same direction and the next one is, then we don't move in that direction. So how did we get to 5? Are we not starting with 0, 0 in the deck? We are not. Should we be? I believe not. I think we saw 0, 0 in it, right? Maybe we should. Oh no, is that it? Yeah, was that it? That was not it. Please tell me that was not it. 1128 is between our 2, right? Okay, 1128 is it. We had the right answer. I don't know what to say. We spent a ton of time debugging something that was basically just, we didn't start with the node. Oh man. Everything was working as expected. We didn't need to make any more changes as of like an hour ago. Wow, that's really rough. Let's get rid of all that massive amount of debugging that I'm going to cut out of the video because it's uninteresting and doesn't do anything for us. All right, part 2 is the lava crucibles aren't large enough to provide an adequate supply of lava. Instead, the elves are going to upgrade to ultra crucibles. I want the Halo announcer to say ultra crucibles. More difficult to steer they also have trouble turning. Once a crucible it needs to move a minimum of 4 blocks in that direction before it can turn, or before it can stop at the end. However, it will eventually start to get wobbly. It can move a maximum of 10 consecutive blocks without turning. So minimum of 4, maximum of 10. So this is just an adjustment to how we generate our nodes. We have to move 4. We can only move 10. I think this is the original example. So this would be, let's copy all this in for part 2. Let's say 94 is the new number. We basically need to do this check in different ways. So part 2 then is going to be, once we're in a direction, so for example, when we start, we have to keep moving in that direction, which means we have to do the same thing we just did, and our vec length has to be, what, at least 6 to determine that, right? Because if this is 1 move, 2 move, 3 move, 4 move, then we also need 5 move to determine it needs to move a minimum of 4 blocks in that direction. So it turns here and goes 4. So that doesn't include this one. So that's 1, 2, 3, 4. We need 1, 2, 3, 4, 5. Wait, so we're already good, actually? This is 1, 2, 3, 4, 5. This is the logic we already have, actually. So 5. So until we hit this condition, we have to move in the same direction we just moved, which means that this is no longer true, but it will be at some point. So up here we do if, I guess we calculate all the diffs early. Basically, this is just going to be an update to our logic here. We already have this logic here. This will work. We just need to work out the cases, which I'm going to do, and then I will show you with the magic of editing in 3, 2, 1. All right, and with the magic of recording, we are back. So the difference between part 1 and part 2 wasn't too bad with the approach that I took. It was a lot of making sure that my numbers were correct, making sure that the tests that I was using were the right tests, tested the right things, that kind of thing. But overall, the generic approach that we took is the same generic approach. The only thing that has changed is which paths are valid. So it took me a little bit of trial and error to figure that out. I changed the diff calculation to be on the entire vec deck that we're just storing, and then we take the first one to see how many are moving in the same direction using dedupe with count, which we'll cover. We're going to do the deep dive real soon. We do a couple of tests against those diff counts. We use those tests to determine which collection we actually need to start with. If we have to turn, we filter out anything that's going straight and we do the others. Otherwise, we can only do the same thing we just did. Otherwise, we can do anything. And for the very first one, none of these will apply because the diffs won't catch. So in our first if here, right up here, if let some diff count, we don't have a diff count if we are on the very first 0, 0 square. So that's living here for that. And then the logic here is basically the same logic. We make sure that the vec deck is long enough. So we change that number that we're checking to see the length of the vec deck before we start popping off. The pop-offs are really important because otherwise these vecs just grow effectively infinitely. I know it's not actually infinite, but if you do not pop these vecs off, you get 60, 70 gigs worth of allocation here. So very worth curtailing that vec growth. But otherwise, this is the same logic. If we make sure that we can't go back to a position we just left, which covers us for the one remaining case we need to remove from these 4. And then the win condition is also different. So we use the same logic we use at the top of the file, and we make sure that the count for the number of diffs is at least 4. So we have to have gone in a straight line for at least 4 tiles effectively before we can even register the goal. So let's start with a deep dive on part 1. We start off by parsing a grid. We do this with a custom number parser. We take the number. We do this by first getting the position using nomlocate. That gives us our ivec2, which we can use that information to get the column positions. And we take one of the numbers. We parse that. It's always going to work because it's advent of code. And then we store the ivec2. That brings up into a hash map, and then we get a hash map of everything in the grid so that we can access everything by key. That access by key is super important because we're going to do things like construct a bunch of ivec2s later, and we want to be able to look into this hash map to retrieve the cost for moving to that square. We get the row count and the column count to determine the grid boundaries, store those in an ivec2 for easy access later. We set the goal to be the bottom right. So that's column count, which is our boundary -1, row count -1. Then we use pathfinding. For me, I feel like there were two crates that we could have used today, pathfinding and petgraph. I usually use petgraph in Advent of Code, so if you want to see petgraph, there's some stuff from last year. Or if you're really interested in it, I could do another video on it. This year we choose to use pathfinding. Pathfinding being more of a ad hoc sort of algorithms crate. So we've got directed graphs and we can kind of build these graphs up dynamically by giving it the successors and whatnot. We don't have to build the graphs up ahead of time, which allows our shortest path here to work in a way where we give it the starting node, we give it how to determine what the next nodes are, and we give it how to test for the goal node. This piece turns out to be really important in part 2, how to test for the goal node. So this actually worked out really well for us. So we use this to start off with a very interesting start position. We don't just start off with IVEC2 splat 0, which is 0, 0. We also keep around a vecdeck. And this vecdeck holds the last n places this search path has seen. That is what allows us to check to see what the next valid paths are. It does mean that we're kind of screwing with the algorithm a little bit. So the way that it determines whether we've covered a place that we've already been is due to the equality trait. So a lot of the places that we would be or could be will now be more unique than they otherwise would be if we only used IVEC2s. So the position 3-3 could be a position 3-3 that we got to from one direction or got to from a different direction. And those would be considered two different places for the purposes of the algorithm. So that gives us the position that we are and the nodes that we've seen up to some count. In our case, for this particular part 1, we keep that count at 5. For the part 2, we keep that count at 14. 14 is a little high for part 2, but it worked out. So we build up each of the 4 directions, north, south, east, west, as an IVEC2, iterate over that, and then filter map. Filter map is important because some of these are not going to be positions that we want to actually advance to, and filter map lets us return none to get those out of the way. We add the diff, so these are diffs is what I'm calling them, for each direction to our current position. We check to see if that position is inside of our grid boundaries, and if so, we continue. If not, this is going to be none. We can't go out into the negative space. If our queue length is greater than 2, then we check the last position we were in and make sure that's the same as the next position we're going to. This means that we make sure that we can't go from A to B and from B to A in the next move. And again, we're returning none here because we're filter mapping, and that takes this position option out of the equation. If we should move forward, we create a new deck that is a clone of the old deck. And this is why it's important to keep the size of these decks down, because if you let these grow, they just keep cloning and growing and cloning and growing. So we push onto this deck and we check to see if the length is equal to 5. All of the decks for part 1 are length 5 or lower. At this point, we do it manually. In part 2, we do this iteratively. But for now, we take the diff of basically the windows of the next 5 items. So every item from 0 to 4 with its next item, we take the diffs. Those diffs are going to be the same values we see up here. So it's either going to be 1, 0, negative 1, 0, 0, negative 1, or 0, 1. These diffs allow us to check if we throw those into a little array here and do .all, whether they're all the same. Now, .all is probably not the best move here because in part 2, we use dedupe with count, and I think that's actually a better option here. Because if we do dedupe with count here, then we get the count of these that we've seen, and thus we could check the number of those. But this worked for part 1. We did them all manually. We checked to make sure they were all equal. If they were, we can't move forward at all. We return none. We take this position out because we can't use it. Otherwise, we pop the extra 1 off the queue, and we return this as a valid next position. Also, if the length isn't 5, we just continue with this as a valid next position as well. Then we need to figure out how to give this to the algorithm to do something with. And to do that, we need to take the position, which is actually, remember, the IVEC2 and the vecdeck, as the first item in the tuple, and then the cost of the next position that we're going to, which is this position, as the second item. We do that by doing this grid get for that position, which is always going to succeed because we made sure that we were always inside of the grid. In this case, we collect because we are generating this data anyway, and we're sending it to the next iteration. And that needs to then build up a new vec deck and a new vec deck and whatever. We're not really referencing much stuff here. We could theoretically reference the ivec2s in the first tuple, but decided not to. So this vec then gets returned from our iteration as the successors. These are the options that we have for the next step. And that happens again and again and again and again. That loops over and over in all different ways until our win condition is settled, which is just that the ivec2 that we are on is equal to the ivec2 that is the end node. That's the simple win condition for part 1. And then we're done. We take the result. This is going to be the vec of ivec2s and vec decks. So it's going to be the entire path that we took to get here, as well as the cost it took to get us here. So we take that cost and we return it, and we're all good. Part 2 includes a couple of interesting additions to how this is supposed to work. The cauldron or whatever now needs to move a minimum of 4 blocks. Once it starts moving, it has to move 4 blocks, no matter what, in a single direction. After that, it can turn. And if it goes 10 blocks consecutively, it has to turn. A really important note that they should have highlighted. I don't know why they didn't highlight this, because all of the other important stuff is highlighted. It's like they're trying to hide it. But once we start moving, it needs to move a minimum of 4 blocks before it can turn. But it also needs to move a minimum of 4 blocks before we can reach the goal. That means these 4 at the end for this second test case have to exist. You have to have 4 segment to reach the end. You cannot get to here and then turn. That does not work. That's why this second test case turns here instead of turning here. So given what we just went over, we use the same algorithm. Everything above this is the same, parser's the same. We switch out the order a little bit. We do the detection of which items or which positions are valid first. So we do our vec deck here. We iter over that with tuple windows, which means we get windows of 2 items. We do the subtraction here and we collect those. So we have a vec of all of the ivec2 diffs that are 1, 0, negative 1, 0, etc. We dedupe those with the count. This is a function from iter tools. This is dedupe with count here from iter tools. Removes duplicates from consecutive identical elements, keeping a count of how many repeated elements were present. So we are allowed to pass it a function to determine whether they are the same, or we can use dedupe with count, which will use equality. So we use the equality version of it, and then we just take the first one. We only care about the first one. We only care about the first, like the last n places that we've been that are all in a straight line. So this will give us how many tiles effectively we have moved in a straight line. If we have it, because we might not, and again, if we don't have it, this runs exactly once to kickstart from 0, 0 to anywhere. If we have that first diff count, then we can calculate the number of consecutive straight diffs, which gives us the calculations for whether we have to turn if we're at the end of our 10, if we have to go straight if we're less than 4, or we could also calculate if we could go anywhere, which is just anything else in this scenario, so we don't even actually use that. If we have to turn, we set it up with these 4 positions, and we filter out the last position we used. So the last diff that happened in our last move is the one we don't want. We have to turn, basically. You might say, hey, Chris, there's still 3 more left, but yeah, one of those goes backwards. We don't know which one yet, so we leave it in, but we will filter that out later. I'll show you. If we have to go straight, then we can only go in the same direction as the last diff, which will be, 1, 0 or something like that. Otherwise, we can go anywhere. We do the same filter map we did earlier with the same calculations for creating the next position and determining whether it's inside of the grid or not. We do the same calculation to make sure we aren't going backwards to the position we just left. We do the same creation of this vec deck, and we do the same popping off if the vec deck is getting too big. All that together, because we've already done the calculation for which positions are valid, means we can just return the next position with the new queue. Everything beyond this is the same. We get the cost in the same way. We collect in the same way. And the only other difference is our win condition. Our win condition requires that we have moved at least 4 tiles in a straight direction. So we use the same logic we did above. We make sure that the count is appropriate before we're testing actually whether we are on the goal tile. All that together works out. And then I've got this print grid, which is pretty nice. Gives me the direction that I took in the paths. I used that for some debugging. It was quite nice. But that's it. That's it for today. I ended up spending a lot of time debugging this, so I'm just going to leave it there. And I will see you tomorrow for the next one, day 18. Have a great rest of your day.